Okay, we're going to move on into 4.9. We actually break 4.9 into two parts, and your lecture packets separate those for you. Uh, and it's sort of a continuation of types of reactions, sort of specialty redox reactions. Now, remember, we had mentioned that there are very few reactions that are not oxidation reduction reactions. So we will continue with that on this guy. So get it to full screen mode here. And the first one is relating to the activity series. You can read through those things. Combustion reactions, obviously, we've talked about before. But the rest of it is kind of a new way of looking at these things. The bottom line is there's sort of a list that we can use that sort of ranks these, especially metals, in terms of their ease of oxidation. So, metal usually has one or two electrons. How willing are they to give up that one or two electrons? So you can come up with a list, and here's the list right here. You think of there's some common sense to this. If you look at the top one is gold, which is not reactive at all. So it doesn't oxidize very much. That's one of the things that makes it such good jewelry. Whereas silver oxidizes a little more, doesn't it? You got to polish that silver every once in a while. And then you go down here to potassium, very, very reactive. And we're going to show some examples of how sodium specifically and some of these metals are so reactive that they will react with water. So not reactive, sort of the WIMPs up here, and increasing ease of oxidation down there on the bottom. So in order for any exchange to occur here, you have to look at this situation. You say zinc. Would zinc be easier to oxidize than copper? And the answer is yes, because it's farther down and it's easier to oxidize. Therefore, zinc would be willing to give up those two electrons, thus making it a positive 2 cation. So you say this will happen. So if zinc metal comes in contact with copper, you will get the copper ions. The copper will fall out of solution. We call this our alchemy lab in general chemistry. It actually looks like the zinc. We put a little blue solution into it, and it looks like it turns into copper. And this was sort of the origins of alchemy, that people thought, look, I turned zinc into copper because these ions stay in solution, and they thought, well, let's figure out a way to make gold. And of course, gold being at the top of that list ain't going to happen. All right. That's and plus it's not alchemy anyway. So if you flip this around and you take solid copper and put it in a zinc solution, nothing happens. It's just the copper just floats right to the bottom. You heat it up. You try to get it to react. It just won't do it because, again, going back to the list here, copper just doesn't want to oxidize as much as zinc does. So it's not, zinc is easier to oxidize, and it's already lost its electrons. So that's not going to happen. So the reverse reaction will not happen. So zinc is more easily oxidized than iron. That's the bottom line. A lot of times you'll see metals coated with zinc because then the zinc oxidizes, and then that sort of offsets the other reactions up there. I have teenagers at home, if you can hear in the background Hey, wait a minute, you guys are teenagers too. Oh, wow, imagine that. So a strip of zinc can prevent that iron from rusting. All right, so if you were going to write a reaction, a copper 2 nitrate solution is poured over solid zinc. All right, so you gotta remember. All right, so you can see this reaction. Oops, sorry. Okay, if you're looking at this reaction, you don't write out the whole thing. You got to jump to really what is the business part of what's going on here. And we know nitrate is just going to stay in solution. We know the copper ion is going to come into play. And then that there's this solid zinc. Well, the way that we're going to approach this now is to write the half reactions to really show what's going on. So the copper is willing to gain those electrons. This is a GER reaction. Whenever the electrons are written on the left side, the copper ion can gain the electrons to form solid copper. So that +2 picks up 2 electrons and forms a solid piece of copper metal. All right, and of course the solid zinc then will undergo oxidation, and zinc is willing to do that. So this solid piece of zinc can lose 2 electrons and under the reaction of Leo. So Leo is a loss of electrons. You can see the electrons are products here. Well, if you look at these two reactions, you line up those yield signs there, those electrons are going to cancel each other out. And the overall reaction then is the copper ion and the solid zinc kind of do the switcheroo. And it looks like zinc magically turns into copper. So that's the real true chemistry of what's going on there. Now, this is talking about halogen. Halogens will undergo this reaction, and this is just their order going right down the row in the periodic table. Notice they are all diatomic, so we're going to talk about these reacting in their diatomic form. So here you have chlorine gas. These are all very hypothetical, very dangerous reactions to do. You can about imagine a green poisonous gas containing potassium and giving off bromine gas at the end. Super nasty reaction. So you're going to bubble this through this aqueous solution containing the potassium and the bromide. Now you know potassium is just going to be a spectator, and you know Cl2 is going to be a gas. So the Cl2 will actually gain 2 electrons, and when it does that, this is just sort of breaking that bond, and then those 2 electrons fill the place where these little free radicals have that 1 electron, and then it jumps on there and quickly forms an ion. Now the other part, of course, is bromine. Br minus is going to turn into Br2, so you'll need 2 of those ions. And guess what's going to happen? Those electrons cancel out. So if you see a reaction that says this, you have to know, I'm not going to write the potassium in there. I'm just going to talk about really how chlorine and bromine are changing places here. So the chlorine gas, this is reduction. It's gaining 2 electrons to be reduced down. And remember, the oxidation number goes down from 0 to -1. Here it goes from -1 up to 0. That's your jumping lion. Leo. Leo means lose electrons or oxidation. And that is your overall reaction. So you've got to tell the whole story of what's going on here. These half reactions tell the story. And on your homework assignments, do that. Show the half reactions as they are used to give the overall final reaction. Now, hydrogen displacement reaction. All right, this one, imagine this. So you have water, liquid water, and you talk the water into giving up 2 electrons. It forms hydrogen gas, which of course we know is flammable, and then ends up with a nice basic solution. That's a strong base right there. So water losing, taking those 2 electrons, and somehow those electrons are worked into this equation of adding these 2 minus charges over here. So somehow, how could you talk water into gaining 2 electrons like this? It doesn't make any sense. So you need to talk about what it is that enables water to undergo this rather strange reaction. Thankfully, it doesn't occur spontaneously. Otherwise, your swimming pool would be giving off hydrogen gas and burning people with base burns as you throw it in there. So here's, and right after this lecture, you get to watch a short video of seeing what happens when you put sodium metal in water. Well, this reaction. That one, you really just kind of have to commit that to memory. You're like, okay, the water's involved here. It's a very reactive sodium metal. So that's going to be the reduction reaction, where it's somehow gaining those 2 electrons. And then the sodium metal will lose its 2 electrons to become ions. All right? When you do that, the electrons will cancel out. And what happens is the solid sodium reacts with water, and it actually kind of dissolves, if you think about it. It's like the sodium solid is now becoming sodium ions, and then it's got hydroxide ions. If you put an indicator in there, you can see that the pH will go up of these solutions, and you get this little bonus of hydrogen gas. And this is a very exothermic process, so it often sparks, and then the sparks ignite the hydrogen, and it often catches on fire. So when we're back in the classroom, you'll have to remind me that we got to show this little reaction of how sodium metal is placed in water to make hydrogen gas. But for right now, what you're going to do is you're going to stop this video, and you're going to see this reaction for hydrogen displacement. Redox reaction. It's a special kind of redox. So you're going to watch a short video where they throw some chunks of different metals into a swimming pool, something I've dreamed about but never done. Okay, so watch video 2 right after this, a short one, and then we'll finish the different types of redox reactions.